Welcome to our submission for assignment 2, where we will be exploring discovering new Twitch streamers. To achieve this, we will be using machine learning to predict user interests. We will cover the steps we took to develop this project, starting with our brainstorming of the predictive task, then a deep dive into the data set we chose through some preliminary exploratory data analysis, then a peek into our model's very own development. And finally, we will end with an evaluation of our model and a discussion of adjacent projects taken with the data that we used. For our predictive task, we decided to create a model which would recommend a new streamer that a user would like to watch based on that user's previously watched streams. To achieve this, we used a dataset of Twitch interactions, which was developed by our very own Julian Macaulay, along with Jeremy Rapaz and Carl Aberer, as you can see in the citation below. Now, the foundational model logistics are based off of concepts utilized for that read prediction task, which you completed within assignment 1. And as a refresher, we were predicting whether a user book pair was a true instance. In our case, that means will a user watch a specified stream, i.e. a user-streamer pair. To evaluate our baseline and improved model performance, we will utilize a similar approach taken in assignment 1, and that was to utilize accuracy and recall. For another refresher, recall is simply the proportion of positive instances we identify within our model over the entire portion of true instances. That is, true positives divided by the summation of true positives and those false negatives. The rationale to recall is that the purpose of this recommender is to maintain user engagement within the platform, which is Twitch in our case. As such, we would rather over recommend and include streamers that may not be preferable to that user than to under recommend and forego recommending a streamer that the user may have enjoyed watching, and thus losing out on that precious engagement we so desire for our corporate overlords. Now, for the key to all learning models and recommender systems, it's ensuring that the model we develop is, in fact, valid. To ensure any model we develop is valid, we must make certain that we do not overfit on that scene data at hand. And as such, we must split the data set into 3 portions. To begin, we must create a 70-30 training and test split to have a final benchmark of model performance on unseen data, which is very important. And then further, within our training data, we will split it into a 90-10 training and validation split so as to measure model performance on unseen data as we are training, which allows us to finish when improvements become minimal on that faux unseen data. Now, let's talk about the data, shall we? With a nice deep dive into its constructions and the basic statistics of our data set. As you may know, our data set is made up of user-streamer interactions on the platform Twitch, which was taken from a 43-day period of observance. For our purpose, we pre-processed this data to sample the very first 200,000 instances, which was just for an ease of use and to maintain the health of our computers. Sorry, I just don't own the San Diego supercomputer, and I wanted to maintain my sanity. For each instance recorded within our data, we have the user ID, the streamer ID, the streamer username, the start period of watching, and the stop period of watching. For simplicity, each period is a 10-minute time frame, with period 1 denoting the beginning of Macaulay's grand observation of Twitch. You may also notice that there are 2 streamer variables. It is important to understand the difference between the two. Think of streamer ID as a unique code for that individual broadcast, i.e. if Ninja were streaming on a Tuesday, whereas the streamer username is unique to that certain streamer, just Ninja. Now, for some data fun facts. Within our sample of 200,000 instances, we have 28,914 unique streamers, as well as 6,810 unique users. For those users, they watched on average 14 unique streamers and watched on average 915 minutes of streams over the 43 days. That's a lot of time spent on Twitch. Now, let's talk about our preliminary exploration and why we did what we did. Based on the construction of our data set, the map of users to streamers can be used to build a model which determines if a user will listen to a streamer they haven't watched before, which was similar to using a map of users and books to determine whether a user would read a book from the unseen data. However, in addition to the user-streamer relationship, we decided we must also conduct some analysis into the user-user relationship using our usage rates. Simply put, do users with similar time on that platform, whether that be time watched or the amount of unique streamers watched, have any relation to the tastes of those users? Let's see. Firstly, we decided to examine the univariate distribution of our usage variables. Notice that they both have a heavy right skew, meaning that there is a small population of users who spend a lot of time on that platform, whether that be the amount of streamers that they watch or the duration of time they watched for. In the final plot, all the way to the right, you can see that there is a positive association between the total time watched of a user and the amount of streamers they watched. But the real question we wanted to answer was, do the users who watch a lot of Twitch and a wide variety of streamers typically watch the same type of content? And do the users who spend little time on the platform and only watch a few streamers fall into that same niche? Well, these plots really don't inform us of that, as they only relate the usage rates to each other and not to the user's tastes. So then to see if the usage rate is at all related to the tastes of our users, we must take a small sample of the streamers that they watch. Within each graph, it seemingly shows that the users with a lower difference between the number of streamers they watch or a lower difference between the watch time have a higher similarity between their watched streamers. However, digging deeper within the data and using a built-in correlation function, we can determine the true correlation between these variables. The table below shows that there is almost no, or a very small negative, correlation between our usage variables and user taste. You can see this through going down the streamer similarity column and looking at the number within the intersection of streamer similarity and diff num streamers and streamer similarity and diff duration. Now, the implication is, well, maybe I wasted a lot of time, but at least we know that user-to-user usage rates have no relation to the similarity and thus do not need to be accounted for within any model that we develop. And in addition, we see that the earlier usage variables themselves are strongly positively correlated, which makes obvious sense, but duh, and not too helpful for our model. However, to get a better understanding of why clustering matters and why we were doing this in the first place, we must look at it in terms of our recommendation and predictive task. So we created a heat map of the top users and the top creators to get a better sense of the possible clicks within the streaming community. As it is clearly shown, there seems to be two definitive gaming communities at the top of the charts. And within these communities, users tend to watch all of the streamers within the click. And so when it comes time to recommend a streamer to a user, we would ideally like it to be a streamer within the click that they watched, but maybe haven't stumbled across yet. Now, to get deeper into this, let's dive into the numbers aspect. And we can look at creator to creator similarity and its implications on the task at hand. Take, for instance, Ninja. For the population of users that watched Ninja's stream, about 40% of that user base also watched Tifu. This could be because they have this stream similar content, or they have a similar streamer personality, or they collaborate together. There could be many variables that influence this. But for us, if we can identify that a user watches Ninja and engages heavily with Ninja's content, i.e., they consume a lot of Ninja streams, or they watch a high amount of time of this creator, we would recommend Tifu if they haven't already watched Tifu, as it provides them with a similar content to what they're comfortable with, while also providing them another outlet to spend more time on Twitch because ultimately that's what matters to us. I hope this left you with a good sense of what our predictive task is because now it's time to look at the models at hand.
So our overall ML task is to build a top K recommendation problem under implicit feedback. In this case, for our baseline model, we're going to be using the rationale that popular streamers are palatable for the wider audience. Our dataset doesn't have a metric for rating, so we're going to be using watch time to substitute for that. Recommendations in this case would simply be the top ranked global creators that the user has not watched yet. So this baseline approach answers the question, what if we ignore personalization completely and assume that every user would prefer the globally most popular streamers? Now, we can go into a little bit of a demo of the baseline code here. So if we take a look at the code, we're first going to be performing a per user train test split and to basically bring in the watch events into training. We aggregate these watch times to get a global ranking of creators. Um, Over here in the recommend popularity function, we're able to filter out creators that the user has already seen and then return the top K remaining streamers. We evaluate this using recall and precision, which we'll go into in the evaluation category. So this baseline is a pretty standard model that doesn't really build into the personalization beyond our recommendation. It's extremely fast because there's no training, but it treats all users identically. And this is not something that we want to do for our recommender system, which is why it's our baseline and we hope to improve upon it. Our problem here is that our dataset only contains implicit feedback. We know that watching a streamer is a positive, but not watching is overall ambiguous. We must predict which new streamer a user is most likely to watch next based solely off of their own past viewing behavior. Thus, we're able to frame this as a pairwise ranking problem instead of your typical classification or regression problem. We chose to focus on the Bayesian personalized ranking model. This is coming from a model that we learned about in class. And overall, the logic is this. We're going to be converting the data into triplets. First, we have our user, then a positive streamer I, and then the negative streamer J. The positive is obviously a streamer that the user has previously watched, where the negative is a streamer that the user did not watch. These are our three inputs that go into our BPR model. The outputs would be a ranking score of you and the streamer for every streamer that the model has never seen for that user. Overall, what we're optimizing is instead of predicting a rating, the model will optimize a pairwise objective function. It'll find every user where the score for UI is greater than the score for UJ for both positive and negative and sample negative items. This objective overall will enforce a relative preference ordering, which is our goal because we're doing a top K recommender system. BPR will learn the latent embeddings for every user and streamer and capture the personalization that we were unable to do in our baseline. It's the appropriate model because it's implicitly designed, or it's specifically designed for implicit models. It scales efficiently with the stochastic sampling that we employ and will produce a high quality ranking. This is the model of choice over classification, specifically because we don't have negative labels and classifying watched or unwatched treats an unwatched as a negative, which is not correct. We can't use regression in this case because there's no target rating that we want to regress to. Pairwise ranking is overall superior because we want to learn the order of preference, not the absolute value. And we want to emphasize that the assumption that all unwatched streamers are equally bad cannot be the case. Let's run through a brief code walkthrough of our BPR model. So after, loading in our data and running our baseline, where we also define a train test split in the function earlier at an 80% and 20% rate, we're going to first create an inner training set and a validation set. Now, we, of course, ran the model without the validation and hyperparameter tuning that I'm going to show you, but we found that it performed a lot better in this case, which is why this is the presentation copy. We wanted to do an outer train test split initially because we want to keep the future interactions separate and prevent any test information leakage. After doing our validation set in order to provide an unbiased metric for our hyperparameter tuning, we're going to move on to ID mappings. So this is the first step in which we just have a lot of different string variations. So we want to make them all into integers for overall model compatibility. Moving on, we're going to extract out a positive interaction dictionary. Now, this is used to create a fast lookup table for which to find all the streamers that the user has watched. And this is going to be essential for our negative sampling that we take forth later on. In the next cell, we're going to build our test sets and define our recall at K and precision at K evaluation functions. So this cell essentially will extract all of the ground truth feature watchers, or all of the true feature creators that will be used for validation and testing. So streamers that the user has definitely watched. And for each user with a held out item, we're going to compare the model result to the true result. And that's how we're defining our precision and our recall that we'll use later on. Now we move on to the biggest part of this code block, which is the BPR class. Now, this is the main model implementation. So over here in our initialization, we're going to initialize user and item embeddings. Next, we're going to sample out those triplets that I mentioned earlier, which are the user, the positive item, and the negative item for BPR optimization. Now, the overall BPR optimization rule that we're employing is that we want to make the score of U and I greater than the score of U and J. So user and the positive item, that score needs to be greater than user and the negative item. So we're going to regularize our parameters and repeat this over 1,000 times. When we're calculating a BPR loss, we're using stochastic gradient descent. So another topic that we kind of, covered in class and updating our latent features as we go on. To end off this cell, we're going to generate the top K creators based on the predicted preference scores. Now, this model will gradually shape the embedding space so that similar users and similar streamers will overall cluster together. That's the goal here, and we're going to generate the top K so that we can, have some sort of personalization in picking what our recommendation, how many streamers our recommendation system will spit out. In this next cell, we're going to move on to hyperparameter tuning. So we're going to try a bunch of different embedding sizes, learning rates, and we're going to evaluate recall at 10 specifically on our training on our validation set. Based on this, we're going to select the hyperparameter combination that had the highest recall in this case. After doing that and solidifying which of our hyperparameters are best for the BPR model, we're going to train the final model on the full training interaction set with an increased number of samples to account for all of the work that we've done up until this point. We're going to produce our final user and item embeddings as a result of this. And lastly, we're going to collect all of our results for recall and precision, and we can, moving forward, compare that with our baseline and evaluate our results. Before we jump into our results, let's clarify again why precision and why recall. We want to evaluate ranking quality, so we care about ranking correct new creators highly. Overall, in our data, users may watch very few new creators, so accuracy would be less optimal in this scenario. We want to judge the quality, so we're going to first look at recall, which measures how many of the user's actual watch creators will appear in the top K recommendations. So we're overall capturing how good the model is at covering those true preferences. Additionally, precision will measure how accurate those top K recommendations are. So it'll answer the question out of the K recommendations, how many were correct? So overall, determining how clean our recommendation list is. Now, if we take a look at our results, on our baseline at with K equal 10, so 10 streamers that we're recommending, we see a recall of 0.06 about and a precision of around 0.01. Now, when we go to our test set on our BPR model, we see at that same 10, we have a recall of 0.18 and a precision of 0.04. So already we can see an about three times three increase across those two metrics. Additionally, the BPR is going to significantly improve pre-call and precision across the different metrics, so 5, 10, and 20. And we do see an increase in recall, which is what we would expect, as well as a decrease in precision if we're predicting more streamers, we're going to expect less of them to be correct just because of the granularity of the specific task. Now, one thing that you may notice is that precision seems kind of low in this instance. Um, we have our best recall at 0.24, but even that seems like it would be low for this model. So how do we prove that this model is actually doing what we want it to do? Now, each user only watches a handful of new streamers in the future, but we're recommending 5 to 20 items. This can cause a lower precision. We're also requiring this model to recommend only unseen streamers, making this task far harder than recommending streamers who they may have watched previously or, ones that they have may just clicked into. We're only recommending streamers that they have never watched before, making this task overall harder. Um, Even though users will typically watch very few new creators and we're only recommending maybe one or two that'll hit, we still consider that to be something of a good creation for Twitch recommending. Exposing users to diverse but related content is something that's going to drive discovery. In the example below for user 329, they've only seen about 5 or 6 true feature creators, which is about where the mean is in our data. When we look at the BPR model top 10, we have about 3 matches, with 0 being in the baseline. Now, it's totally possible, and it is the case for many users where they only have one true feature creator, and sometimes we're not able to predict it even though we have 10 different predictions. Just because the number of streamers that we are bucketing is low, and we need to predict between 5 and 20 will cause our overall precision and recall to be on the lower end. But since we're improving so significantly over our popularity baseline, we can be sure that this form of recommending is actually doing a justice and a benefit to the users that will use our product. With To wrap up, popularity is providing a trivial lower bound, and we have BPR significantly improving both precision and recall. And for an example here, we have qualitative reasons showing that BPR capturing the niche tastes that the baseline might miss. With BPR, we're successfully able to learn meaningful user preference patterns in our implicit data. Our personalized model is significantly outperforming our popularity baseline and providing better quality recommendations for new and unseen streamers.
Finally, let's discuss why we have this data set in the first place. This data set was developed to train the model LiveRec, which delivers users live recommendations of streamers to watch based on their history on Twitch, as well as the subset of streamers who were active at the time of recommendation. Similar to our goal of providing users new streamers to watch, LiveRec accounts for the dynamic nature of Twitch with a temporal feature to account for streamers who were live at the time of making the recommendation, while also utilizing watch time or repeated watching as a dominant signal for user preferences.